So how's chemistry like making a peanut butter and jelly sandwich? That's what we're going to find out today. We're going to be talking about limiting reagents and stoichiometry. So we'll take a look at this, and if we are going to make, let's say we're going to make a peanut butter and jelly sandwich, um, we could write an equation for a peanut butter jelly sandwich. We could take, of course, we have our peanut butter. We could add in our jelly, and then of course, we'd have to add in 2 pieces of bread, and we put all those together, and our product is going to be a peanut butter and jelly sandwich. So down here, of course, we've got our, our peanut butter. We've got some strawberry jelly, and we've got a loaf of bread. Now, with this loaf of bread, let's notice that we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Say we have 16 pieces of bread. So if we were to make a peanut butter and jelly sandwich with 16 pieces of bread, and we were only using 2 pieces of bread per sandwich, we'd only be able to make 8 total peanut butter and jelly sandwiches. That would be it. We would run out of bread and wouldn't have any more bread. And what we're talking about here and how this relates is if we run out of bread first, we're still probably going to have jelly left over. We're still probably going to have peanut butter left over. But if we run out of bread, that essentially stops the production of peanut butter and jelly sandwiches. Chemical reactions are real similar to this in that sometimes one of the reactants, much like the bread, can run out, stopping the production of any product. So let's talk about how this relates to chemistry. So a couple terms that we need to be aware of. First off is a limiting reagent. A limiting reagent is going to be also known as a limiting reactant. So we have to think of these guys as reactants. And this is going to be the reactant that is consumed or the reactant that runs out, essentially stopping the production of whatever your product is. It stops the chemical reaction from occurring because there's no more reactant available, much like the bread. We also have excess reagents or excess reactants. These are going to be our reactants that remain after the limiting reagent has been consumed. So in these 2 examples that we were given before, our bread would be our limiting reagent. It stopped the production of peanut butter and jelly sandwiches. And of course, the jelly and the peanut butter were left over at the end, given that we started with, let's say, a full jar of peanut butter and a full jar of jelly. Okay. Something that's really, really important that we need to know, how to spot a limiting reagent problem if we're given a limiting reagent problem. And the biggest thing is there's usually 2 known values given. And a lot of those stoichiometry problems we've been doing recently, they will give us the word excess for one of the reactants. And if they give us the word excess, it means we have plenty to go around. We do not have to worry about one of the reactants running out. Okay? So that's the way you're going to spot it, 2 known values. And so let's take a look at a problem that is essentially a limiting reagent problem. So in this problem we have 25 grams of magnesium metal reacting with 2.5 moles of hydrochloric acid. So right there, this should tip us off. We have 2 knowns. We have a limiting reagent problem to deal with. And then it's asking us for what volume of hydrogen will be made. And it's nice that they tell us at STP that lets us use 22.4. Then, so we're looking for volume in liters of hydrogen gas. And then it's also going to ask us to identify who's the limiting reagent and who's going to be the excess reagent. So there's a lot of things going on here. Now, because we have 2 knowns, what we're going to need to do is we're going to need to do 2 stoichiometry problems. So we're going to start with 25 grams of magnesium metal in our first stoichiometry problem, and we're going to want to work that to liters of hydrogen gas, and then we're going to start with 2.5 moles of hydrochloric acid, and we're going to work that also to liters of hydrogen, because that'll tell us something very important. So let's go ahead and do this work here. So a grams to moles conversion for magnesium would be 1 mole of magnesium over the molar mass of magnesium. 24.31 grams of magnesium is equal to 1 mole. Our mole ratio of hydrogen gas to magnesium is a 1-to-1 ratio based on those coefficients in the balanced equation. And then because we were at STP, we can use 22.4 liters over 1 mole to finish that off. And I'll go ahead and run my other, set up my other problem before I run some numbers here. We're starting with moles of hydrochloric acid. So we're going to want a 2 mole of hydrochloric acid to a 1 mole of hydrogen that is our mole ratio to get us converted. We don't need the molar mass here, obviously, because we're starting with moles and not grams. And then we're going to go 22.4 liters over 1 mole. And so let's go ahead and run some of these numbers and see where where it comes out. Okay, so I ran those numbers, and for the first reaction, I've got, or first stoichiometry problem, I got 25 grams of magnesium producing 23 liters of hydrogen gas, and then I have 2.5 moles of HCl producing 28 liters of hydrogen gas. So the question was, what volume of hydrogen is made? Now we have two answers, and how do we choose the right one? Well, it's easy to choose the right one. Whoever or whichever answer has the smallest value gives us the right answer. This tells us this is the amount made. So we made 23 liters. Now the reason behind that is at that point, once 23 liters was made, the magnesium was used up. So there was no more magnesium to keep going. We couldn't have kept going to 28 because all of the magnesium was used up. And so that tells us right there that the magnesium, the reactant, is the limiting reagent or the limiting reactant. And the hydrochloric acid was in excess. So this is going to be our excess reagent or excess reactant. Okay, so that's how we determine how much is made based on a limiting reagent problem. Let's take a look at one more problem that takes us a step further and asks us to calculate the amount remaining of the excess remaining reagent at the end. So here we go. We're given a reaction. We have 2 aluminums reacting with 3 copper 2 chlorides to form 2 aluminum chlorides and 3 solid copper, 3 moles of solid copper. And so we're starting off with 9.5 grams of aluminum and a half a mole of the copper 2 chloride. Okay, so right off the bat, once again, 2 knowns, we've got to have a limiting reagent problem. So we're going to do 2 sets of stoichiometry problems individually. 9.5 grams of aluminum, and they're asking us to calculate the grams of copper metal produced, which is our product. And so I'm going to do a grams conversion of aluminum to grams of copper. That's going to be my first starting setup. And then it also asked us to do 0.5 moles of the copper 2 chloride. And I'm going to do the same thing. I'm going to go out to grams of copper. Now I could, if I was only being asked to calculate the limiting reagent, I could just go to moles. But in this case, the problem asks us to go to grams, so we might as well go to grams. So we're going to do this calculation. 1 mole over the molar mass of aluminum, which is 26.98 grams of aluminum. And then we have mole of copper to mole of aluminum on our mole ratio to convert between those two. Looking up above, we have 3 moles of copper per 2 moles of aluminum. Now we're going to finish this all off with the molar mass of copper being 63.55 over 1 mole. And we'll run that in a second. We're starting off with moles, half a mole of copper 2 chloride, so we're going to have moles of copper to moles of copper 2 chloride from the balanced equation. We have 3 moles of copper to 3 moles of copper 2 chloride, so a 3 to 3 ratio, and finish it off 63.55 over 1 mole of copper. Okay, so let's run some numbers here and see where we're sitting. Okay, so I ran those numbers there, and so I came out with 33.6 grams of aluminum using our 9.5 grams of aluminum to start with. Sorry, this is incorrect. This should be copper, and this should be copper. We're going to copper. And so 33.6 grams on the first one, 31.8 grams on the second one. So we would say that the lower of the two is the amount made, the smaller value. And that's going to let us know that copper 2 chloride was our limiting reagent. So we'll just actually, I'm just going to write this down here, part B. Limiting reagent was our copper 2 chloride, and our excess reagent is aluminum. Okay. Now, the next problem is going to ask us calculate the mass. I'm not sure why that's back to A. That should be C. Calculate the mass in grams of the excess reagent remaining. Okay, so we want to figure out how much aluminum still remains after this reaction occurs. And so what we're going to do is yet another stoichiometry problem to figure this out, and then a simple subtraction. So to map this out, what we're going to do is we're going to take the mass of our copper made, and we're going to work that backwards to the mass of our aluminum consumed, just using stoichiometry. And then we're going to subtract the mass of the aluminum consumed from our original mass of aluminum, and that'll give us the mass of the excess reagent remaining. So let's look up here. Once again, we started off with, we produced 31.8 grams of copper. So we have 31.8 grams of copper being produced. And we're going to work it back to the mass of our excess, which is grams of aluminum. And this is going to be consumed. So 1 mole of copper over 63.55 grams of copper. We're going to do our aluminum to copper ratio. Oops, let's make that a U. And then we're going to do 26.98. I'm just going to scroll up and double check my aluminum to copper ratio. Aluminum to copper ratio is a 2 to 3 ratio. 2 to 3 ratio. Let's run some numbers here and see where we're sitting. So there's my numbers. I came up with a value of 9.0 grams of aluminum being consumed. And so, but the problem actually does ask for the grams of the excess remaining, not consumed. So we have to be careful of what it asks. So let's do this. Let's go 9.5 grams of aluminum, which was given in the original part of the problem. That was our starting point with aluminum, and we consumed 9 grams of it, so it's obvious that we have 0.50 grams of aluminum remaining. So if we actually measured this out, in a beaker, let's say we had a beaker, kind of model this out a little bit, with whatever value we have here, where we have 0.50 moles of our copper 2 chloride solution, and we threw into this beaker 9.5 grams of aluminum. Sorry about that. Let's make that 9.5, not 9.0. It looks like it. 9.5 grams of aluminum. After the reaction was completely finished, what we would have left over at the bottom, we would have 0.5 grams of aluminum remaining, and we would have no copper 2 chloride left. Everything would be converted to aluminum chloride in the solution. So that's kind of modeling that out, what it looks like there. Okay, and so essentially, once again, limiting reagent is going to be our reagent that runs out, reactant that runs out. Excess reagent is going to be our whatever's left over at the end of the reaction, and we can use stoichiometry to calculate it. And as I said before, the way you determine if you need to do 1 or just 2 stoichiometry problems is look for the knowns. If you have 1 known with excess, the likelihood is you have just a regular stoichiometry problem. If you have 2 knowns, we should just cue into the fact that we've got a limiting reagent problem in our hands, and we need to do 2 stoichiometry calculations to make sure that we get to our proper answer. And that's it for today.